I assume by now everybody knows a lot about the double slit experiment, so I'm going to go through this very quickly. If you take elementary particles, quanta, photons, electrons, and so on, you send them through two slits, and you look at a screen to see what happens. If you don't know which of the two slits the particle went through, then you get an interference pattern. And this, of course, works just as well if you're sending a single photon or single electron at one time. The mystery is that as soon as you do know, by any means, which of the two slits the particle goes through, then you get a pattern that looks like it's particles. This is, of course, leads to the famous wave-particle duality. And in a much more practical sense, it leads to this sort of thing. The caption says, it says the cost of the flight went up because we acknowledged its existence. So there's something peculiar about observation. And this is, of course, the quantum measurement problem, which has been described before here, but I'm going to do it in a simpler form. You have some sort of a system, which could be a double slit, any kind of physical system, some sort of measuring apparatus. And the measuring apparatus does an observation of the system. From a quantum perspective, you take the tensor product between the two quantum systems, the two physical systems, and you end up with a system and the measurement apparatus no longer being independent. So we can say that the two physical systems are entangled. So from a quantum perspective, we're just dealing with complex waves. There's no particle-like behavior yet. John Bell made this sketch to illustrate the problem. Well, where does the measurement end? So if you imagine that you have a photon and it goes through two slits and it hits a screen, you might have a photodetector, and then you might have a counter that looks at the number of times that the photodetector goes off, and then the human eye and the human brain. All of those are physical systems. All of them are therefore quantum. Well, why do we see a particle? Why does observation make a difference? So this is sometimes called the von Neumann chain or the Heisenberg chain. Where is the cut made? When does quantum become classical? John von Neumann said that the measurement chain ends only when knowledge of the measurement is registered by what he called an extra-physical factor. In other words, you can't use another physical system to end the chain because it just becomes more quantum. So you need something extra-physical, by which he meant consciousness. And he wasn't alone in his opinion. Almost all of the founders of quantum mechanics said something like this in various ways, but go all the way back to Bohr and even Planck. They all said something like this, and this continues to the present day, as you know. This is today a minority opinion within physics, but nevertheless, it has a pretty prominent background. So I've been aware of this, of course, and everyone offers theories about consciousness, but nobody does anything about it when it comes to this particular problem, the measurement problem. So what we did in the laboratory is we built a double slit system, and fortunately it's a very simple type of a system. You have a laser, you have a filter, you have a double slit, and you have a camera that looks at the result. So the only new element in this experiment is that we ask people, in this case like a meditator, to keep the double slit in mind and to imagine in their mind's eye that they could see which of the two slits that the photon went through. This is, as far as we could tell, the only way of directly testing whether consciousness is actually collapsing the wave function. So this is what the apparatus looks like. The tube sticking out of the long box there is the far end of the helium neon laser, and the double slit and the camera are inside the box, so it's a sealed system. You can't see it with your eye, you can only use your mind's eye. This is the camera. It's called a line camera, and this particular one is 3,000 pixels long in a line. And what the camera sees is an alternating band of light and dark. This is the interference pattern. When you look at this in software, you can say, well, how bright is each band? And you get a picture that looks something like that. Does that show up? Yeah. So you get this sort of Gaussian-looking shape, and that's the way of looking at the interference. So if we start with that pattern in picture A, you can do a Fourier transform, which is picture B, and the peak in the middle is now the double slit spectral power. And this is the way we initially started doing these experiments, with looking at the power spectrum. And this is convenient because, again, we ask someone who, in this case, in the laboratory is 2 meters away from the sealed optical system. We ask them to keep the double slit in mind. And then the measurement is very simple. We predict that if observation is doing something to the interference pattern, that the double slit component of that interference will go away, or at least it'll go down. In addition, because this is an abstract task, the double slit itself is about, each slit is 10 microns across. And if you simply hold up the double slit to somebody to have them look at it, they may or may not even be able to see it. So it's difficult for some people to imagine that they can, in their mind's eye, see what's going on in that space. So we do a real-time analysis of the double slit power, and we use that to adjust feedback tone. So if you have somebody doing the task, they could look at a screen, which is showing a signal, or they can simply do it by listening to the tone. And generally what we do is we have like a droning tone, and we ask the person to make the droning tone louder, make it just louder because it's a very pleasant tone. And then that if they would know that they were succeeding through that tone. This also provides a way to focus their mind on the task at hand, because mind wandering is always a big problem. The protocol is very simple as well. We compare the double slit power during mental observation versus no observation. They get a voice message which says, now concentrate, and then now relax, and this alternates. We do the observation periods for 30 seconds, and the rest periods are 30 seconds, plus or minus a random 5 seconds, for reasons I'll mention later. This is repeated in a typical session 40 times. So the whole session lasts 20 minutes. And the measure that we're interested in is a differential measure. We're asking, what is the double slit power while observing versus while resting? So that, and there are many ways of doing the statistics. We generally present it in terms of a z-score, or an effect size. So we did our first experiment in this form. This was for 35 sessions, 20 minutes apiece, 15 people contributed it. Overall, you can see the mean and one standard error. We did actually pretty good. Meditators did a little bit better than the non-meditators. And the prediction was that the double slit power would drop during observation, and indeed that's what we saw. So when we do experiments of this type, especially when they work the first time, we're always suspicious about the first timer's effect, or everybody's very enthusiastic about what's going on. So we repeat it again and again. So we did 4 pilot studies, each time adjusting things in various ways and looking at different kinds of aspects of the design. And in each case, each one of the 4 pilot studies, the meditators did quite well. If you just combine everybody, the green dots are the overall result, and in some of the experiments, the non-meditators did not do very well. They tend to mind wander pretty quickly. So there's as you remember, there's a 30-second period where you're asked to do this abstract task of putting your mind in a box at a distance. And they can do that for about 4 seconds, and then they can't do it anymore. So the overall result of the pilot studies was this. You see, again, overall, we got a pretty nice effect. Meditators did quite well. Non-meditators overall got actually close to chance. And we ran the same system. And this, by the way, was 250 20-minute sessions, 137 people. And we ran the same system again and again as controls, which are the white dots. And we don't see any artifacts within the hardware or software or analytics that would suggest that there's some kind of bias in the system. So here it looks like observation was collapsing the wave function. At least the meditators could do that. And the control tests, we don't see any effect. So we were encouraged by this to go ahead and do a formal experiment, formal in the sense that we pre-specified how many sessions we would do in advance, so 50 sessions. So here's the result of the 50-session pre-planned experiment using the same analysis that we had used in the previous experiments. And this gave us a 5 sigma result. So for those of you who are not used to the term sigma, think of it in terms of z-score. It's the same thing, standard normal deviate. So we got a 5 sigma result when people were observing, and when nobody was doing the observing, we got almost exactly chance. When we do an experiment like that and we get a very strong result, if you keep in mind that a 5 sigma result was able to give CERN the Nobel Prize for finding the Higgs particle, which turned out not to be Higgs after all. Well, we got a 5 sigma result too, but I haven't heard from the Nobel Prize Committee yet. And we were also suspicious of it because that seemed way too good. So we did another formal experiment. Again, 50 sessions. We did other things I don't have time to talk about on this. But one of the things I'm showing here now is this is the control results, and it's lagged in time. And the reason why we look at the results lagged in time is because if you ask somebody to now concentrate, and then a little while later, now relax, you can't switch your mind instantaneously. So we expect that there should be a delay in the results of the experiment because it takes the mind to switch gears. So this provides actually a nice secondary way of looking for the results that we hope to find, because if there is no delay, then you have to be suspicious about the results. So here's time 0, which is when the instruction is given to switch your attention. There's the experimental results with the lag from 0 to 15 seconds, and in fact, we got a slightly better result with 2-second delay. So I'm not going to talk about this analysis again for the remainder of the experiments, but we did this sort of lag analysis in all of the studies that we've done. So after doing the second formal experiment, again getting over a 5 sigma result, we got suspicious. So maybe this was caused simply by proximity of the human body. Even though it's 2 meters away from the double slit system, we figured that maybe when somebody's asked to concentrate, they lean forward slightly. And for those of you who've worked with interferometers, you know that they're exquisitely sensitive to everything. So we thought maybe the temperature change from a body 1 inch closer versus 1 inch away would be sufficient to make this result. So we decided to put the entire thing on the internet so we'd be sure that we could rigorously separate people by distance. So there's the double slit. This is sitting on a rack that has a bunch of servers on it. And we ran this for 3 solid years, calendar years 2012, 13, and 14, ended up with over 5,000 sessions done by human observers and 7,000 done by robot observers. And I'll explain what that means in a minute. So when somebody would sign on to our website, this was a public site, by the way, we got people from around the world to do this, in a non-observing condition, what you would see is this blue rectangle on the browser screen and simply saying, please relax. And you'd hear no sound. And then it would switch. You'd hear a voice saying, now please concentrate. And then you would start seeing this line move along the screen. The instructions were to make the line go up. And you would hear a kind of a whistling sound that was a tone. And the tone would go up and down as the line went up and down. And we did that so, again, you could do this experiment with your eyes closed. There were also lots of checks and balances built in here. We knew, for example, if somebody left the experiment while it was going. And we would then we'd restore all the data, but we'd mark it as this was an experiment that was not completed by a person. For what we call the robot experiment, it was a Linux system which was designed to simulate a human. Now, the beauty of this is that everything was exactly the same as far as the double slit system was concerned because it didn't know, we think, it didn't know whether a human was looking at it or a Linux system because they both came through the internet in the same way. So we have very nice control for human observation versus we don't know whether a Linux system is conscious or not, but if it is, it probably doesn't have the same level of consciousness as a human. So here's the interference pattern. This is the central portion of the interference pattern that the camera would see. What we did on this was a simpler measure than we did before, and this is called fringe visibility, which looks at a peak and a trough, and it measures the relative difference between the two. And this is nice because if you work with lasers, you know that they're not amazingly stable. Some of them are more stable than others. We were using a helium neon gas laser, which is known to do things like mode hopping. Power levels will slightly change. And you have to jump through some statistical hoops in order to reduce the effect of that mode hopping. But for fringe visibility, you don't need to worry about that so much because this is now a relative measure and takes into account that there may be fluctuations in power. So it's a more sensitive measure as well. So the prediction is fringe visibility while you're observing would go down. So it's somewhat similar to expectation that double slit power would go down. In this case, it's fringe visibility. So this is the result of the sessions in 2012. There are 2,303 sessions done by the Linux system. These are the middle 20 fringes of the interference pattern. And it shows in terms of z-scores where it was. There's one or two of them that were around 3 sigma, but overall it was pretty close to chance. And this is what we got with human observers. So some, again, approached 5 sigma differences. That was 2,089 sessions by 689 people around the world. So what's nice here is they're able to look at yet another issue, which is, does distance matter? So this is the distribution of the effect sizes from where we were in California to the farthest that you can get from our laboratory, which is South Africa.